Again, we'll start the talk. So welcome to another Ryan Science Club talk. The RISE Club is a self-organizing initiative that is entirely early career researcher-led. We host weekly seminars that aim to raise awareness and provide training in reproducible, interpretable, open, and transparent science. Before I introduce this week's speaker, I would like to remind everyone that there will be a Q&A session after the talk. During the talk, people can ask their questions by using the Q&A column on your right side of the screen. And then at the end of the talk, I'll ask those questions. If you see a question that you would also want to ask, I would ask you to press the like, and we'll try to start with the most voted questions. So today's speaker is Dr. Aaron Caldwell, who is an exercise physiologist with a Ph.D. in health, sport, and exercise science from the University of Arkansas. He's currently an ORISE Postdoctoral Fellow at the United States Army Research Institute of Environmental Medicine, where his current research projects are focused on human performance in extreme environments. Aaron also works as an applied statistician. He has gained expertise in statistics through a graduate certificate in statistics and research methods program while at the University of Arkansas. And he's continuing his education with an M.Sc in analytics through the Georgia Institute of Technology. Today, Dr. Caldwell is going to talk about the Superpower R package, but I'll let him tell us more about it. Aaron, I'm just going to ask you to share the screen, if you would mind.
There we go. Can everybody see my slides?
Hold on a second. So slides, and then yes.
Perfect.
Hold on a second. Here they are. Yes.
There we go. All right. So hi, everybody. Thanks for coming today to hear me talk about one of my passion projects, which is the Superpower R package. You know, if you're not someone who codes in R, do not worry. I've tried to develop some tools that are more point and click. So this still applies to you. And, you know, and even if you don't code in R, hopefully today will be maybe some motivation too, because, you know, simulation can be a very powerful tool if you do know how to code. You know, just a few years ago during my Ph.D. studies, about halfway through my Ph.D. studies when I kind of started to learn how to code. And, you know, there was a time where I had no idea what simulation was, and that was only, again, like about 4 years ago. So, you know, if you don't underestimate your ability to be able to do exactly what I've done here today. Quick disclosures, nothing today represents the position of the Department of Defense or the Army. It's kind of a boilerplate statement that I always have to give with these talks, just so everyone's aware. And then we can kind of jump right into it. And, you know, why is this important? Why do we care about, you know, simulation or power analysis in general? And so I just want to do a quick refresher, just so everyone's aware. If you've seen some of my previous talks on this, a lot of the first half of this talk is going to be retreading some of the same material, but I have some new stuff towards the end that should be quite interesting. So I'm sure, as most people are aware, if you've done any type of statistical analysis, when we're using frequentist statistics, or the frequentist kind of paradigm for statistics, we're concerned with two types of error, type 1 and type 2. So just as a refresher, type 1 is a false positive, type 2 is a false negative, and we control those by setting acceptable alpha and beta levels for our study. And so when we're justifying our sample size, what we're saying is, given a specific alpha and a specific beta, we'll have the ability to detect an effect. And statistical power is 1 minus that beta. And one of the things I want to emphasize here is that statistical power is a hypothetical probability of detecting an effect of a certain magnitude. right? So it's hypothetical in that we're saying we would, we want to detect an effect of this magnitude. So it's very conditional on whatever, the effect size is and your alpha level is. And if we have no effect, it's equivalent to the alpha level itself, right? So if there's no effect in the study, you have your alpha set at 0.05, your power then is equivalent to that 0.05, in which case that's also a false positive. And so the real question is, why do we care about these numbers? Why should you even be concerned about statistical power, type 1 and type 2 error rates? Well, the main thing is both we as scientists and our funders who are giving us the money to do these studies want to find effects if they do exist. And this becomes important because if we are interested in a very small effect, or even noisy effect is another way of thinking about it, and collect a small sample size, then we are unlikely to detect that effect, at least with a low alpha level, that is. So we can even adjust that type 1 error rate, as a way to compensate. So it really becomes important and justifying to our funders and even to our ethics approval boards that yes, if we do the study, if we use these participants, if we use these resources, we have a good chance of actually finding what we say we want to find. And one of the things I want to mention here, and this is something probably a little bit more specific to I think some of the things that have happened in exercise science in the past 2 decades, there's no free lunch in statistics. Bayesian analyses or other analyses are all going to run into the same issues about being able to detect or reliably estimate the effect we're interested in. So, I would say be very wary of any type of statistical test or hypothesis test that claims to magically be able to allow you to have a lower sample size. There are some design options you can make, but statistical tests in general, there's no magical option that allows you to have a very low sample size. So some visualizations of what I mean when I talk about statistical power. And this is actually derived from a simulation, a custom simulation I ran, but you can get a very similar plot from the Superpower package. And this is the distribution of p-values. So in this case, this is 100,000 simulations in 3 different conditions. The first one up top here in A is the distribution of p-values when the null hypothesis is true. When the null hypothesis is true, all p-values are equally likely. Right? And I think this is kind of a misconception that at least I had when I was first learning statistics, is that, if the null hypothesis is true, the higher the p-value. That's not necessarily true. It's just very unlikely, if we have a low alpha threshold, that we would then have a low p-value, right? And then, if the alternative hypothesis is true, and we have 50% power, lower p-values are more likely, and as power goes up, the more likely we're going to have a p-value below that threshold, right? So the skew really happens with power. When there's no power or the null hypothesis is true, all p-values equally likely. So traditional power analysis, I think a lot of people tend to use GPower. What you do is you find your effect size of interest. That needs to actually be defined. In many cases, we're interested in comparing 2 groups or within individuals between 2 conditions and looking if there's a change in the mean. And so what you do is you calculate a standardized mean difference, which usually is the mean or mean difference divided by the pooled standard deviation for independent studies or independent samples design, or the standard deviation of the differences if you're using a within subjects or paired samples design. And one of the things I would mention here, whether you're simulating or not, this should almost never be a previously observed effect size. So you should be going out into the literature saying, hey, previous study found Cohen's d of 0.175. That's the effect size we're going to use for our power analysis. That's not a very good thing to do, because what you may be interested in, you may find it relevant to have an effect size smaller than that previously reported effect size. And if you use the previously reported or observed effect size, you're going to be underpowered to detect those smaller effects. With GPower, what you enter in the standardized mean difference, you then set a alpha and beta level, and then a sample size is given to you as output. And so just as a quick refresher for some of you, or if you've never used GPower, the output looks something like this, or the interface looks something like this. You can select your statistical tests or family of statistical tests over here, and then you can even select a type of power analysis. So I would say 90% of the analyses I see out there is typically an a priori power analysis, and typically either the mean differences or the mean differences between two dependent means. And all you have to do here is select the tails of the test. So is it a 1 or 2-tailed test? Most cases, I think people use a 2-tailed test. You then set the effect size. So, we may be interested in a larger effect size, right? We're only interested in effects that are Cohen's d 0.8 or above. For this within subjects design, we can set the alpha level to whatever we want. So we don't even have to set it to 0.05. We can set it to 0.045. And then the same thing for power. We could set it to where we want 91% power. And then we can calculate it. And then what it tells us here is that we would need to collect 20 participants to have at least 91% power, what we put over here, with the alpha set at 0.045, right? Pretty simple, pretty straightforward and quick. I think the issue, though, as I'll get to it here on my next slide, is that how do we extend this to more complex designs? A lot of people use ANOVA for their designs, or they have some type of factorial design where it's, a 2x2 is very popular in my field, for example. The effect sizes in these cases are much less intuitive. So, previously I was talking about mean difference divided by the standard deviation. That's, I think, fairly interpretable for most people because it's essentially the effect over the noise, if you will. But then you get, into these more advanced design, and the Cohen's F is what's used. And then it becomes a lot less intuitive. What does a Cohen's F of 0.1 mean, right? What does it mean for your design? What does it mean for your hypothesis? And I've very rarely had a researcher tell me exactly, what their hypothesized effect should be on this scale. So I think it, becomes more difficult. So my partial solution to this is to use simulation. And in particular, I created the Superpower R package and Shiny web apps to help with this process. And, it's specifically for, normally distributed data for factorial kind of analysis of variance designs. So how does this work? You define a design. So you essentially set up how many factors you have. So, is it a 2x2? So that would be, 2 separate factors, each with 2 levels, or is it, maybe a 3x2 design? You then set the population. Once you set the design, and that gives you kind of a grid of cells. You then set the population parameters. And for this, you set the mean, standard deviation, and covariance, which is input as the correlation between within subject. This is only for within subjects designs. One of the things that this kind of program assumes is that all the data is derived from a multivariate and normal distribution. And this has a lot of major assumptions that may not be true for some hypothetical designs or phenomena. But I think for the most part, it's still very useful. And then the way simulation works is you define the design, you set the population parameters, and then it runs a simulation, essentially generating random samples from that population that you've defined. And then what it does, it essentially then, if you've set an alpha, it then counts the number of results that make it below that alpha level, right? And then it gives you a power calculation saying, if you do it 1,000 times and 900 come back as below the alpha level, then it will say, yeah, you have about 90% power, right? And then it also now can calculate confidence intervals on that because, right, we've collected random samples, so we can even get a confidence interval on that power for the given parameters you set. This is also very nice because it allows us to adjust for multiple comparisons. So we could even do, like, say, a Tukey post-hoc correction for maybe some post-hoc comparisons of interest, and it can take that into account because it'll correct the sampled from each simulation p-value and then correct it, and then it will do the counting. So it's pretty useful in kind of seeing what effect your multiple comparisons corrections have on power. So how do you use this? I can show you the code, but I think a lot of people. Let's see if this works. It will not. Okay. Let's go here. Yep. There we go. A lot of people find this more intuitive than the code itself. So this is what the web app looks like. You simply can go to design, and then you just have to go through this list of questions and input the appropriate information. So let's say we have a 2 between 2 within subject design. So you could think of this as almost like a parallel groups design. We have 2 groups randomized at baseline, and then we get pre and post measures on them for this outcome of interest. You can set factor and level names. We're going to skip that for now. And with the Monte Carlo simulations, this kind of repeated sampling simulation, you can even set different sample sizes per cell, so long as it's all between subjects. So in this case, we can't. So let's just say we're going to put 25 participants per cell. So in this case, that would mean that we have, 100 observations, but 50 of them, it's only 50 subjects, or no, 25 subjects in each group in this case. And we just measure them twice because there's that within subject factor. Let's say the common standard deviation is 1. So one of the assumptions of ANOVA is that you have homoskedasticity. That essentially means homogeneity of variance between all groups. We can violate that assumption in the simulation, but for the most part, I would say, avoid doing that unless you have a good reason to believe that that's the case. We can then set the common correlation for within subjects factor. So in this case, the pre-post correlation, set that to 0.65, which may or may not be reasonable. And then we can set the cell means. So first off, I'm just going to set up the design like this, right? All is ones. It seems to have put in our correlations correctly. We have a regional variance covariance matrix, and the model seems to be correct. Now we can set the different means. So let's say we start off at 1 for both groups, and then for one group, we go up to 1.25, and then for the other group, we go up to 2. Perfect. And so then that's where we see A1 goes up to 1.25 at B level 2, and A2 goes up to 2 at B2. Okay. So once that's all set, we can go over to the power simulation side. You can set a seed for reproducible results. That essentially means if you use the same seed, it's going to give you exact same output again. I don't tend to do that. You can select different sphericity corrections if you're using within subjects ANOVA. In this case, because it's only 2 levels, we don't need to worry about that, so we're not going to do that. And then estimated marginal means, that's the EM means if you use SPSS output. So we can do specific comparisons of the individual cells if we want. For multiple comparisons, we're not necessarily worried about that. And let's just do, let's say 50 simulations real quick, just to make it quick. And then we can set the alpha level, let's say at 0.07, just for funsies. So we let it run, gives us a little counter at the bottom, and then it gives us an output, right? And something I need to update here that's not on the Shiny server yet is that it'll even give you a confidence interval over here on the results. Essentially indicating, if the confidence interval is really wide, you may need to up the number of simulations to get that confidence interval a little tighter. But you can run these small simulations to get an idea of what the power would be around for those population parameters. And what's nice is you can download a nice little PDF report. Perfect. That gives you all the output. And this is something I've actually seen people put into their IRBs, right? Or even funding agencies as far as detailing exactly what their power analysis was. All right, so back to the slides. And so one of the main issues you may see with this is we ran 50 simulations right there. That took about 5 seconds to run. You probably should be doing about 1,000 to 2,000 repetitions for a Monte Carlo simulation if you're trying to estimate power. And those take a little bit of time to run. It's very useful, but one of the other things we can do to kind of make the process quicker is to use an empirical distribution. And this essentially means that when we simulate, we're not randomly sampling from a population, we're actually setting the mean standard deviation and covariance to the specific values we set. We can then get the effect size estimates and then back calculate what power would be for a given sample size. But being faster does come with costs. Complex designs can't have small sample sizes. That's actually been overcome with the ANOVA exact 2 function, so you don't need to necessarily worry about limitation 1. And limitation 2 is there's no correction for multiple comparisons, so that's out the window. And I would also add in here limitation 3 is you can't violate assumptions for ANOVA. So like one of those is you can't put in multiple standard deviations when you're doing the empirical type simulation, because otherwise it's going to give you bogus results. Well, the function right now will just, if you use Superpower, will just not let you do that. So I'll show this real quick. Again, back over to my website. You can just switch over to exact. Looks very similar. It's pretty much the same thing, except we have less options now, right? And that makes sense because we can't make a lot of the, violations of assumptions and all of that. We can then put in, I don't remember what sample size I put in over here. I think it was 25. Oh, not 215, 25. We didn't want any of that. 6.5, and then it is 1.25 and 2. Yep, always check that plot. Sometimes for whatever reason, I don't know what the issue is that I've coded in here, but sometimes it doesn't update the design when you click the button the first time. So you may have to click it again. We then can go over the exact power tab. Once again, we'll set this to 07, runs, and just like that, it's already done. And we can see here the results somewhat differ from the results we saw in the ANOVA Power app. And that's because, we're taking random samples. Like I said, most likely the confidence interval for those results would include 89.69, right? Because we only ran 50 simulations. This will be on, as long as you're not violating any assumptions for the analysis of variance, this will always be the exact correct result first time you run it, right? Very accurate, very quick. We just have less options. All right. So that's the exact example. But there's a lot of key questions. I get emails all the time asking me different things about Superpower and how to use it. The most common question is, how do I know what my mean, standard deviations, and correlations should be? That's a very good question, right? There's no Cohen's D scale of, 0.2 standard deviation is small, large, or whatever, right? It's going to be specific to your measures, your design, all of those things. But one of the things I want to remind you is that power is a hypothetical probability, right? So what I would suggest doing is, if your hypothesis would be true, what would be the, smallest differences in means, largest degree of variance or largest standard deviation and lowest correlation, let's say. I would also say be skeptical and select reasonable parameters. What is your most skeptical reviewer going to think? Are they going to think that, these standard deviations are too small, your means are too large, and your correlations are too optimistic? If that's the case, then you should probably rethink it. So I would just think of whatever your biggest critic's going to say. That's what I would put in as your parameters for the mean, standard deviation, and correlation. But the advantage of doing it this way is the presentation to funding agencies, IRBs, and pretty much everything else as far as justifying your sample size will be much more straightforward, because you can essentially give them that little plot of the design, variance covariance matrix or correlation matrix, and say, given these parameters that we've outlined, this is what we want to be able to detect. We expect to have adequate X power, whatever power you get from the functions, with a sample size of X per group or condition, depending on the type of design, at an alpha level of Z, right? Boom, one sentence, you're done. And then it's up to the funding agencies, IRBs, to then state whether or not they believe that these parameters and alpha level are reasonable. And I've gotten sometimes pushback on both. I think this is also very good because it's a rather intuitive way of presenting your design compared to the non-intuitive standardized effect size. If someone tells you, oh, we're powered to detect, 85% power to detect a Cohen's F of 0.25, I don't think many people would really know if that's reasonable or not. But if you show them, the expected patterns of means, variance, and correlation, I think they would be much better at judging that compared to the standardized effect size in this case. So just makes it a little bit easier for everybody in understanding what you're trying to detect. So another thing you can do with Superpower is balance your alpha and beta error rates. So one of the things I think a lot of people consider is they just go out, they select, I want 80% power, 5% type 1 error rate. We're essentially implying that type 1 errors are 4 times as costly as our type 2 errors. And just, here's the effect size, give me the sample size that I need to collect. And I don't, we're essentially ignoring 2 different things that can be dynamic when designing a study. And I would say many times this balance of errors, that 1 to 4, just isn't the case. There are many times where we want to have type 1 error and type 2 error be exactly the same level. So we've also kind of created some justify your alpha type functions. So I will go to those now. So ANOVA compromise, I've already run this one. So we can put in a design, something like this, very similar to what we had before, except the patterns of means are a little bit different. And in this case, we have 20. And maybe in this study, we can only collect 20 people for each group, right? We just are like, resources, money, time, that's all we can do. So then you can just put in the parameters just like this, get your design, and then you can go to the Find Alpha tab. And it'll give you a couple options. Do you want to compare estimated marginal means? In this case, no, we care about the ANOVA level effects. We can then tell it, what's the relative cost of these two errors? Are they both equally as costly? The default is yes, they're the same, so 1. And we can even put in prior likelihoods, right? And 1 right now, again, we're saying they're equally likely. And then you have 2 options for how to balance your alpha levels. Or your alpha and beta level, which is the minimal approach, which essentially says what alpha level would minimize the combined error of the alpha and beta errors, right? And that even takes into account likelihoods and costs. Or we can look at balance, right? So that's kind of the typical way of doing it. So if we can say 1 to 4, so we would put in 4 in here in balance, and then it would essentially say at what alpha level would, give us 4 times the beta error rate, right? But I think minimal is probably more the best approach. And for this design, we can see over here, if we're trying to detect the interaction, an alpha of 0.1 actually is going to give us the optimal combined error rate, right? That's where that's minimized. Any higher alpha level, the combined error rate raises. Any lower alpha level, and we're going to start losing power to the point where the combined error rate raises. So you can write this up where you say, we're limited to this certain sample size. This is what we believe the parameters are, and at this alpha level, we're balancing our errors. We're minimizing both our type 1 and type 2 errors maximally. All right. So big update for today. As of this morning, version 0.1.1, which I'm calling Black Canary. It's a Superpower package, so I've got to give it superhero names, is now out on CRAN. So what's new? Mostly it's just some bug fixes, small little things that I found when going back through the package like I always do. But in addition, the big 2 are that you can now get confidence interval output for simulations. So anytime you're doing those repeated repetitious Monte Carlo simulations, and then this new feature called Mori plots, which allows you to see your power level given a design at different levels of effect size. So I can pop over to R here real quick to show you what that looks like. So I've got some scripts here that will start running. So there's 2 Mori plot functions that have been added, one for t-tests and one for f-tests, right? So you can put in an effect size, a sample size, and again, that sample size per cell. Alpha level, so you can put in multiple alpha levels, the type of t-test, and the alternative hypothesis. So in this case, we have a paired t-test that's one-sided. We want to see the power at 2 different alpha levels, 0.05 and 0.075, at 2 different sample sizes, 10 and 20, with an effect size between 0.1 and 0.5 Cohen's d at these different intervals, and that's just more for plotting purposes. So we can just do that real quick. And it gives us these pretty plots, at least I think they're pretty, maybe biased because I made them, that look like this. And so essentially what you can do is, if you're ever, this is something that you could probably do more post hoc, which is, we had, these 2 different sample sizes at these 2 different alpha levels, and we can see what the power would be to detect, different levels of effect size. So as we go up the effect size larger, the higher the power, right? And even alpha level higher power. And what you could conclude from this is, at n of 10 and n of 20, we're just not really able, at highest is 0.075, at a sample size of 20, and even then the power is below 80. So what you could conclude from these plots is, this design, even at n of 20, really isn't going to be able to detect anything reliably below Cohen's d of 0.5, right? It's one way to look at it. Another is the F-test plot. The thing that stinks about this is the way these F-tests are calculated. It's in numerator and denominators degrees of freedom. So there's a little helper tab on the website that I'm working on that'll help you calculate what the numerator and denominator degrees of freedom are for your given design. We can put that in here. And it gives us a very similar plot, but then it's giving a grid here of different denominator degrees of freedom and different numerator degrees of freedom, right? And given a different Cohen's F effect size, and Cohen's F 0.5 is quite large, typically. But even there, again, at the sample sizes we've given, mainly determined by these denominator degrees of freedom, we're really underpowered to detect any of these effect sizes less than 0.05 once again. All right, that's what this looks like. It's just another way of kind of thinking about power in the sense of ranges of effect sizes in this case. And then the other new feature is the confidence interval. So we can, create a design just like this. This is actually from one of the vignettes of the package. Gives us a little design like this, calculates power like it just did very quickly with 100 simulations. And then we can take that power analysis result and it can output confidence intervals on those results, right? So at 100 simulations with these parameters, we can't really rule out at a 2% alpha level the power being lower than 9% or greater than 23% for the voice effect, and the same thing goes for the interaction. Or like, let's say emotions are our biggest one. We can't rule out that the effect size is below 80%. So what we may do is go back, increase the number of simulations to get tighter confidence intervals, or we may modify the design in some way to see if that will help raise power a little bit. All right, back to the slides. I promise there'll be time for questions here very soon. I just want to get through kind of everything Superpower does. And I do want to answer some common questions that I get to kind of get those out of the way, but I'll try to go through these as quick as possible. How do we achieve good power for both main effects and interactions? Again, this is kind of my boilerplate response: is find the comparison of interest with the smallest effect size, and power your study to detect that effect. Or if you have a primary outcome, if the primary outcome that you need to demonstrate has an effect for your hypothesis, then you should power for the interaction. And you may even want to adjust your alpha for different types of comparisons. You don't have to have one alpha level for the entire study and all of the outcomes that you're looking at. And then another thing I would mention is, yeah, the package only really covers ANOVA right now, but it doesn't mean you can't simulate for a regression, and you can write some custom code, and I'll show here shortly how to do that. So if you're not using an ANOVA model, don't try to fit that kind of square peg into the circular hole. Go use some other tools. There's more complicated designs that you may be worried about or have concerns about. One of the things I would mention is we're actually working on an entire book that covers pretty much everything you need to know as far as simulation goes. So aaroncaldwell.us/Superpower Book. Anytime you have like a specific design question like this, you can just go to that link and you'll have a plethora of examples. I will warn you, it's still in development, so it may be a little sparse as far as the text that you'll be able to read and how we explain it so far, but we're working on it. Again, as I mentioned, if you're conducting experiments with very rare populations, so I work in exercise and sports science, you may be dealing with elite athletes, which is very narrow population. So you only may be able to collect, if you get 10, 12 participants, that may be a lot, if not impossible to go higher than that. So again, I would highly suggest using that justify feature to then see what alpha level or balance between alpha and beta level is going to be the most effective for your given design. And then here's a common question I get is a lot of people doing like essentially reaction time research where they have a number of trials and stimuli, right? So it's a multi-level design. You have participants who are getting participants within stimuli within trials, or flip that. And a lot of people try to use ANOVA on this data, and what they do is, you end up averaging or aggregating these responses in the subgroups. I would recommend against doing that. ANOVA is probably not appropriate. It's not going to be your most statistically efficient tool. It is complicated, but you can use packages like SimStudy and Simmer and R to do something like that. And I actually have some examples in my code here. Scroll down, and don't worry, this is a lot of code here. I get it. This is all just using SimStudy first, and then we're using Simmer at the end to create the simulation. So all you have to do with a package like this is use the def data function, as well as some other functions to create kind of a simulated data set. So in this case, what I was always taught up with multi-level models was kind of the school aspect. So you have students within classrooms within schools, and those may be assigned random treatments, the schools may be, but you still want to take into account the effect of the individual students as well as the classes and even classroom size. So what we can do is first generate the school itself. So we have, a degree of variance at the school level. We have a number of classes, which, in this case, we assume a non-zero Poisson distribution for the number of classes within each school. So we start by generating that. You take a quick look at it, right? We have the number of classes, school level intercept, and then we can even assign a treatment. And so it's now randomly assigned each one of these randomly generated schools with a treatment. We can then generate a class, same thing, maybe a little bit lower variance within classes. Again, we can then set a formula to generate class sizes. So we can go through all of that and add that to our simulated data set. And then we have the exact same thing. We now have our school level intercept, our class level intercept, the number of students within each class, and then we can even generate the student level data, right? And in this case, we're hypothesizing some effect of the treatment group on our outcome variable of interest, a fixed effect of treatment group, and a overall kind of grand intercept of 50, while also incorporating these two random effects, and then an associated variance with the student level data as well. And we can generate that again, and then this gives us, our final data set, if you will, in a data table format, right? And then let's say it's test scores, and then we have our simulated test scores here at the end. You would analyze this data with something like a mixed model with LME4's limmer function. That gives you a nice little, output like this if you specify the model in this way. But you can use something like, this is just a random simulation, right? So it's not necessarily reflective of the effects at the population level, although you can see from up above, they're fairly close. We can define what we actually expect those population parameters to be with the make limmer function from the sim-r package, right? So we essentially define the exact same model formula as above. We then put in the fixed effects. So instead of these rounded values, we put in the 50 and 8 that we have up above, and then we can put in the variance levels that we also see for the variance covariance matrix. And then we can also put in the residual variance here as well. Put that in, we can look at it. So it looks almost identical to what we see above, but we've actually set all the parameters to exact values now. All right, and let me actually run this real low because it may take a while to run. So don't do this if you're actually trying to justify your sample size. I'm just doing this to speed up the process so we can actually see what the results are in real time. You can actually thank the SimR package for why confidence intervals were added to Superpower, because I got the idea from them first. Perfect, so it's built all that, and we can then print the result, right? And then it shows, right, in this case it's saying 100% power, right? In this simulation, all the results came back positive, and then we have a confidence interval of 78 to 100, right? So at 5% alpha, we can't rule out a power less than 80%. So my suggestion in this case would then be to, increase the number of simulations. Just realize it may take a little while. Okay, so that's custom code. highly, highly, highly recommend using this approach for very complex designs. Another function we're working on, I'll actually get to questions rather than showing it, is how do I find the right effect size or patterns to match an effect size? You know, you may really not have a good idea of what the right patterns of mean or standard deviation are, and you kind of may want to look at what the Cohen's F effect would look like. And so we're actually working on a function now where you can put in the Cohen's F effect size, and it'll give you a pattern of means and standard deviations that would correspond to those effect sizes that you put in. And that way you can kind of see like, oh, does, you know, that magnitude of difference, does that make sense as far as what I'm visually seeing now from the function? So that may be kind of helpful in kind of gauging what you expect to find. So some concluding remarks before we get to some questions from the group. Simulation is a powerful tool for estimating power. It's not just limited to power. You can use it for many other things. So you can violate assumptions, like I mentioned earlier. You can violate the assumption of sphericity, homogeneity of variance, and you can actually see what effect it has on your type 1 error and how much that will inflate and whether or not your model will still be good. You know, if you're assuming that some of these violations may occur. You can also use it to get a accuracy or Bayesian power analysis. So you can essentially simulate and see, like, are the confidence intervals going to be thin enough of the time, or from a Bayesian approach, is the posterior probability, you know, going to be high enough for my given hypothesis enough of the time with a given sample size. Another great thing about simulating, so like that custom code, it's a great way to set up your analysis pipeline. So all of that model stuff that I wrote out, you can then just port that over to when you're doing the analysis, and boom, you already have your code written. You just, the data is going to be coming from your raw data rather than from the simulated data. So that can be quite nice and make your process easier. And then one of the things I want to remember is, you know, don't forget to justify your alpha and power levels. They're not fixed values. So, you know, use that to your advantage. So one of the things I do want to mention is thank you to the U.S. Army Research Institute of Environmental Medicine and all my colleagues there, as well as my mentor, Nisha Charkoudian, and all of them tolerating me babbling about simulation all the time. I also want to give a shout out to all the collaborators that have helped with the development of Superpower. Daniel Lockins has been instrumental. Frederick Aust, you can thank for the estimated marginal means. Lisa DeBryan was absolutely instrumental in kind of debugging our very early versions of this package. So big thanks to you, Lisa. And then a big thanks to my stats professor at the University of Arkansas, Dr. Ronna Turner. Without her, I would not have had this idea. All right, I'll take any questions.
Thanks, Aaron. That's a fantastic presentation.
Thank you. Sorry, it was a bit of a fire hose of information there.
Sorry, just trying to. Don't think people can see me yet. Oh yes. Yeah. No. Like I was saying, really nice presentation, because really nice balance between your explanations and then practical examples. There are some questions. I think you answered some parts of the questions, but I'll let you decide if you want to expand a bit more on them, or if you feel like you have answered the question totally. Just 1 second, because I'm trying, not entirely sure, but it's not letting me get Aaron on the actual image. So the question, the first one I was going to ask, I think you mentioned already at the end, but so Charlotte asks, Charlotte is explaining that she has used your Superpower app with mean and standard deviation based upon her own previous research, but in the case that there isn't any previous data, how do you know which mean and standard deviations correspond to a certain effect size difference? And the example is Cohen's d of 0.20.
Yeah. So this goes all the way back to, I mean, previous research can definitely inform what you're doing here, right? Like, for example, like you can do a pilot study if you don't know what your outcome of interest kind of looks like. You can do a pilot study to get an idea of what the variance will be, maybe correlations between repeated measures, if that's the type of design. But one of the things, I think you really have to consider with power analysis, it's all about hypotheticals, right? And if you're using your previous research, you really should be saying, I saw a 7-point increase with a 7-point standard deviation. Boom, that's what my next study, I'm going to power my next study to find that. Because I would ask you the question, all right, let's say you observe a 4-point increase in your next study with the same standard deviation, or maybe even double. Would you still be interested in that effect, right? And if you are, then you should have powered your study for the latter case, right? That 4-point and maybe 14 point standard deviation, right? So it goes back to this kind of whole idea of smallest effect size of interest, right? It doesn't matter what previous research has shown necessarily if you'd still be interested if the effect size was smaller. So again, use your previous research to get good heuristics and ideas of what your data is going to look like. But I would definitely set up those means and standard deviations, again, based on the kind of more skeptical notion of whatever is the smallest effect that you'd be willing to report and say is proof or a severe test of your hypothesis.
Thanks, Aaron. Another question, and apologies if I'm not pronouncing the first name correctly, from Mircea, is does the design tab on the Shiny app that you were showing us, does it accept nested designs? And the example is 2 between by 2 within by 2 between.
Right. So no, not currently. So that's a little bit more difficult, and something, I take that suggestion in stride because it's something we thought about when we were designing the app, but it's one of those things where it adds a degree of complexity that we weren't able to make it where it would be user-friendly still, if that makes any sense. So no, what I would suggest doing in those cases is doing exactly what I demonstrated very quickly, I know, but writing out custom code where you're actually writing out the different levels of error, generating a sample set and then running that sample set through the SimR package. Or you can even write your own custom for loops where you sample, and count the number of significant results, if you will. So yeah, you're gonna have to write your own custom simulation in those cases, to my knowledge. Or if you have a previous data set, you can use that as a proxy. And then the SimR package can do all the heavy lifting for you. Yeah, so sorry, and I will say that feature is probably not going to get added to Superpower anytime soon.
Sure.